Hey, what's up everyone? Jason Turley here, and it's been a while, but I am finally back returning to the ROP Emporium series of challenges. I knocked out about 3 of them and kind of just gave up on the series, so I do apologize. I have been working on a side project that I will hopefully reveal, but let's continue on. We're on write4, so if this is your first time looking at ROP Emporium, let's actually go back to the main website real quick. So they are a collection of challenges to learn return-oriented programming, which is a way to get around an exploit mitigation called data execution prevention or non-executable. Essentially, whenever the stack, which is a program of process memory, is marked as non-executable, because normally you would just write your shell code, you'd overwrite the return address, and then you jump either back inside your buffer or a little bit outside your buffer, and you would land inside your shell code, and that would give you remote control access to a computer or run whatever command you want. Data execution prevention and NX are security mitigations that prevent just executing data on the stack as code. So we have to get a little bit creative, and the technique to bypass that is called ROP and ROP Emporium. The website we're on now, it's a series of challenges that get a little bit difficult as you go on. There's 8 of them total. I already have 3 on the channel, and now we're going to knock out some more of these. So we're going to go on with write4. And it says, so our first foray into proper gadget use. A useful function is still present, but we'll need to write a string into memory somehow. Okay, so the main, I guess, goal of this is to be able to write some type of string into a memory location. And then it gives us the option to download it. We've been rocking and rolling with the x86 64, so the 64-bit series of challenges. So we're going to continue doing that. Chord cut. On completing our usual checks for interesting strings and symbols, we're confronted with the stark truth that our favorite string, binCat_flag.txt, is not present. So we can't simply call bincat on like the flag file and print it out. So it won't be that simple this time. You'll see later that there are other ways around this problem, such as resolving dynamically loaded libraries and using the strings present in those. We'll stick to the challenge goal, which is learning how to get data into the target's process virtual address space via the magic of ROP. Awesome, and then it goes on to talk about some of the differences, and it highlights here, very important. So there is a function called print file. It does exist within our binary. You can call it with the name of the file you wish to read, like flag.txt, being the first argument. So print file, if I had to I guess assume, it probably does something along these lines. So it's called print file. It takes one argument, which is called a character pointer file name. And this is just pseudocode, but it likely opens up the file, it prints contents, and then it simply closes the file handle. So we need to call print file, and we know in x64 the first argument of a function is in the register RDI. So RDI should be the first argument. And that's really all we have for now. We know the file name is called flag.txt. We need to somehow pass this into RDI. So you might be thinking, all right, cool. So let's just make a ROP gadget. So if this is our stack, we have like our padding, and we overwrite the base pointer, and now we're at the stack pointer, and then we just put something like a pop RDI instruction, and we pop the value flag.txt into RDI, and then we simply call print file. So this way, flag.txt would be stored inside RDI. However, this would be storing like the literal string flag.txt, the literal, I guess, bytes. What we want, because this is taking a character pointer, and what is a pointer, right? We know that pointers are simply an address that stores a value, right? So instead of hard coding the string flag.txt, what we really want is to pop into RDI the address that contains flag.txt, something like that. Address that points to flag.txt, or address that contains it, however you want to word it. But we don't want the hard code digits flag.txt. That's not going to work. That's going to cause a segmentation fault. What we actually want is to find some type of address, some pointer, right, where we can write flag.txt and then pop that into RDI. So this is missing some things. It doesn't seem like the binary has flag.txt anywhere in there, like at any offset. If it did, this would be a simple challenge. So we need to find some way to read or somehow to write flag.txt to a memory address. And I believe that's what it's pointing at here. It's telling us, hopefully you've realized that ROP is just a form of arbitrary code execution. And if we get creative, we can leverage it to do things like write to or read from memory. So that's awesome. So it does give this like a generic example of move, and then in these square braces, register the value of this. So essentially what this is doing, whenever you see square brackets around something, it's a dereference. Similar to like an array in C. So if you have, this is getting a little sloppy, a little ugly, but if we have an array or a list, whatever you want to call it, 1, 2, 3, you can say array at like 0, and this will give you the value of 1. Right, so it's a dereference, it's accessing something. So whenever you see these square brackets around a register, an assembly, you're either reading or writing to the actual memory address that is stored within that register. So hopefully that made a little bit of sense. And then it goes on and it tells us, yeah, we know we want to call a print file. You can consider wrapping your write gadgets in a helper function. If you can write a 4 or 8 byte value to a location in memory, you draft a function using Pwn tools that takes a string and memory location and returns a ROP chain. That's kind of neat. Let's see if we are able to accomplish that. So with all that talking out the way, let's actually start to, I guess, analyze and debug this file. So I'm already inside my ROP Emporium folder. You can see it's been a while since I've made any videos, dating back to July and September. So let's download this zip file, ls. So we need to extract it. So unzip write4. I'm going to actually do attack D to specify an output directory. That way everything gets written here. Let's remove that zip file since we no longer need it. And now we can start rocking and rolling. I'm just going to do a file star to figure out, hey, what exactly is in this folder. So if you've done capture the flag challenges before, typically you need to find the flag value. In ROP, they just give it to you. They give you the flag, and it's your job to exploit this binary to get it to print out the flag itself. So we have 2 binaries here, 2 elfs. The top one is lib4write.so. File extensions don't really matter that much in Linux and Unix land. However, we do see that it is a shared object. And if you're not familiar with what that is, all a shared object is, it's very similar to a DLL in Windows. It's just additional library code. It might have additional functionality that this binary needs. It is 64-bit. It makes sense. And it's dynamically linked. Both of these are dynamically linked. Dynamic versus statically linked. If it's statically linked, it contains all of the library code it needs inside the binary itself. Whereas dynamically linked, it doesn't. It needs to look around and find different functions and different like system calls and whatnot that exist within the shared object or library file. And neither of these are stripped, which is awesome. Something not being stripped, all it means is it still has some of those debugging symbols and that useful information. So if we open this up in a debugger or disassembler, you will see like main, and you will see something called like print file, and you will see the names of the functions. If this was stripped, we wouldn't see that. It would just be like generic fun underscore some number or sub for subroutine. It would be a little bit tedious and harder. And since these aren't necessarily reverse engineering challenges, they're binary exploitation challenges, they're giving us a little bit of help by not stripping the binary. So now let's actually analyze it. So I like to do Robin2, which is a tool within the Radare suite of tools. It's a reverse engineering framework. And I like to just run tac capital I, just to see, hey, what is this file? We can look at the architecture, we can look at the file size, but what we really care about is some of these file permissions. NX, non-executable, is marked as true. So we know we have to use return-oriented programming. We can't exploit it any other way. And that's really all we care about. We already know it's not stripped, it's not static, it is dynamically linked, and it does use virtual addressing. Is there anything else we need at this point? Let me think. If we do a tac little I, that will just show us some of the functions that exist in here. So we do know that there is something called pwnme, and let's do the same thing for that shared library object. Okay, so it calls, like, I guess just regular libc functions, printf and memset and read. So nothing insane. Let's actually run it. Go ahead and give me the input already. It's pretty aggressive, isn't it? Let's say please sub. It says thank you, but it doesn't print out a flag. So we know we need to exploit it. Let's see. And just for completion, if I do wrap this in strace and I scroll up to the top a little bit, if we look at these calls for open at, we do see it does open up that shared object from earlier. Whatever, quit out of this. Now let's open this up in GDB, which is the GNU debugger. And if you look at mine, it is a little bit different. The prompt says GEF, GDB Exploitation Framework. It's a plugin I have installed. So let's disassemble main. Okay. All main really does is call a function called pwnme. So let's look at that. Let's disassemble pwnme. There's nothing really here, but we can see here it is in the procedural linkage table. So I guess this is the true address of it. Let's actually run the binary. Or before I do that, let me set a breakpoint. Breakpoint on pwnme. Now let's run it. And it's going to print out a lot. That's because I'm using GDB enhanced framework or exploitation framework. I forget what the E stands for. It's either enhanced or exploitation. And it just makes things a little bit more suitable for reverse engineering and exploit development. For example, I ran the binary and I hit my breakpoint. You can see here, stopped at this address inside pwnme because we have a breakpoint, and it prints out the contents of all of my registers, which is really nice. I don't have to do that manually. And then it prints out a few sections of what is going on the stack. So we can see the current instruction that is about to be executed, move EAX into 0, or move 0 into EAX, yada, yada, yada. So it's just nice. If you've never used GDB before, I wouldn't recommend using Jeff. I'd recommend starting with vanilla GDB with no plugins or anything like that, just to get the hang of it. So now I'm hit, let's actually do the disassemble so we can look at exactly what's going on inside of this function. Hopefully everyone can see that. So at the very top, you can usually safely ignore some of this. It's called the function epilogue or the function prologue. We're just pushing the base pointer on the stack and we're setting it equal to the stack pointer. But here, this is interesting. We see a subtraction on the value OX20, hex 20. Let's print that out. What is hex 20? So print as decimal OX20, 32. So we're allocating 32 bytes on the stack. And if we scroll down, we can see the name of different functions, set virtual buff, put string, so just print out some values. It's just printing out that prompt we saw earlier. But here's what we care about. We see this call to memset, and if we look backwards, we can see the arguments being passed to it. So the first argument is RDI, and we see RDI is being set to RAX, and up here RAX is being set to whatever is OX20 subtracted from the base pointer. So this is our buffer. ESI is 0, and then EDX is 20. So we're calling memset on buffer. This stores our user input, 0, and then 32. And all that is doing is clearing out our buffer, making it all zeros, because in C, you're never guaranteed for anything that you allocate to be empty. You need to explicitly mark it as empty or clear it out. And what else do we have? Okay, it does some more printing, but we care about this, read. This is where our user input is stored. So it's calling read RDI, or EDI in this case, is being set to 0. So it's reading from standard input, a 0 is standard input file descriptor. The second argument, RSI, is being set to our buffer. And then the last argument is OX200. So there we go. There's the typo. They're setting it to OX200 instead of OX20. So they're actually allowing us to read into up to 512 bytes into a 32 byte buffer. So there we have a buffer overflow. Since I am using Jeff, we can simply do pattern create 100, and it's going to grab a pattern of 100 bytes. Now we can run it. Let me actually delete this breakpoint. We don't need it anymore. Hit C to continue. It asks for our user input, so we give it 100 bytes of this generated pattern. And we can see here, down here, write4 stopped at this address inside the function pwnme. Reason sig_seg_v, so segmentation fault. All that means is we've overwritten some critical values on the stack, and the program really doesn't know what to do anymore. It kind of crashed. So if we scroll up a little bit, where do we want to look at? If we look at RSP, the stack pointer, or we could just look down here at the actual contents of the stack, we see that we have overwritten a lot of values. The stack pointer is now pointing to our garbage, our junk. It's expecting some type of address to return to or some type of data, but instead it just has this garbage. It's not really sure what to do, and it's seg faults. So here it actually prints out like the ASCII, and then here is the hex. OX61 is lowercase a, so on and so forth. And then we actually see the new line character, OX0A. So we know we've written this far. So here's what we want to do, right? We want to fill up our buffer, which is 32 bytes. After the buffer is going to be something called the base pointer. And if we scroll up here, we do see that the base pointer was completely overwritten. Right after the base pointer is something called the stack pointer, which points to where the program is going to continue execution, right? So we know the buffer is 32 bytes. On x64, every register is 8 bytes. So the buffer plus the 8 bytes of the base pointer, 32 plus 8 is 40. So we know it takes 40 bytes of junk, of whatever, to get to the stack pointer right here. And hey, I don't like math any more than you do. So instead of actually doing that in our head, instead we could have done something else. We could have done pattern search for $RSP, and it will look how many bytes it took to overwrite the stack pointer. So we see here that it took 40 bytes. That was simple. We could do the math ourselves. But if you don't want to, if you want to save a little bit of brain power for later on, you can do pattern search with whatever register you're looking for. Nice. So we know we can override it with 40 bytes of junk. And now we need to actually start passing in our ROP chain. We need to start telling the binary like what we would like it to do. So what gadgets can we use? This is ROP Emporium, and they do have some hard-coded like functions and niceties in here. So if I clear my screen, Control L to clear, and I do disassemble useful, and I just hit tab twice, we do see it auto-completes. There's something called useful function and useful gadgets. So if we look at useful function, it does set up and then call print file, right? And we like print file, so we can save this address for later. We don't need the address as useful function. We can just grab the address of print file. So let's see, examine 8 instructions from here. And we do see that it is print file. So it's just printing out the contents of whatever we give it inside RDI. What else do we have? We have useful gadgets. So let's disassemble useful gadgets now. Okay, so we have this instruction here. And we saw that earlier in like the intro, where we're moving, in this case, whatever is inside register R15, we're taking that and we're storing that at the address. So R14 here has to contain an address, right? And like this is an address, for example. This is an address. So R14, go to that address and write it there. You're referencing a pointer, essentially. Okay, so there is no flag.txt string, so we need to write that ourselves. And this is the instructions that they're giving us. So what we need to do is two things, right? So we want R15 to equal flag.txt, that string, and we're going to write it to some type of memory address. So R14 will contain the memory address, R15 will contain the string. And if you're curious where these registers came from, R14 and R15, if I do an IR, which is just short for info registers, which prints out the state of our registers, we see that there are a number of different registers we have in x64. So if you're coming from x86 or maybe even ARM, the register names are going to be different and the number of registers you have to work with are different. In x64, we have multiple general purpose registers. We have AX, we have RBX, and so on and so forth. We know RDI and RSI contain the first and second argument to a function, but we also have these general purpose ones. The ones essentially just extra, just scratch space, just like throwaway registers that you can use here and there. So R8 through R15. Why does it start counting at R8 and not R1? I have no idea. So those are just extra registers that we can use within our exploit, within our program. So trying to keep track of all of this in our head, it might be a little bit cumbersome. So let's actually start building out our exploit script. So I like using Vim, but Sublime Text or anything else works as well. So let's make our shebang line, user bin env python 3 from pwn import all. So this pwn, our pwn tools, is a framework usually for capture the flags. It just makes things a little bit easier for generating exploits and making exploit code. So we know we have our padding, right? It's going to take 40 bytes of whatever. I'm just going to use A's. And let's actually write down some of these memory addresses. So we know we will need this instruction here, R14 and R15. So let me grab this address. I'm just going to call this write what where. And I wrap this inside of a function called P64. So it'll take this hex and it'll actually convert it to like a byte string that our payload will understand later on. What else did we see? We saw the address of print file. Let's just grab that now. Print file equals P64 of this address. Okay, let me actually make a comment so we know what this is. Move into R14, whatever is in R15. So we know we need to be able to store something in R14, and we need to be able to store something in R15. So let's make a note of that. When we call print file, we kind of notated over here, RDI will be the first, or it only takes one argument. So we need a pop RDI instruction. So let's make a note of that. We need to find a pop RDI instruction later on. What else do we need? We need a writable address. Writable? Not sure you spell it. Writable address. Writable memory address. So this is what will be inside R14. Let's clean this up just a tiny bit. So R14 will contain the memory address. R15 will contain literally flag.txt. RDI will also have that address, right? Because it takes a pointer. And then we need to call print file. And then I guess we can do like padding. So this is essentially how we're setting up our stack, right? Setup for stack. So we have our padding. We need to pop an address into R14. Cool. I think this is good. Let's just rock and roll. So we're missing a few things. So we need this writable memory address. So inside of Jeff, you can do a function called info proc mappings. Ooh. Here, let's there we go. Hopefully this is clear to see. There we go. Hopefully that's easy to see. So info proc mappings are, you can just do vmap, print it out in color. So we need to find a memory address that we can write to. So we can see that there's a lot of different addresses. We see the start and we see the end, and then we see the permission. This is what we need to pay attention to. So R and X, you can read from it and you can execute it. You can read it. Here we can read and write. So if we actually come down here and we look at the stack, remember we saw NX, non-executable, enabled? Well, if we look right here, we see the permissions are read and write, but executable is turned off. That's why we have to do ROP in the first place. So we need to find a writable address. I guess we could do this. We could just write to this shared object, this library, but I don't really like that. Just in case like ASLR, address space layout randomization, was on and these addresses change on every run, it wouldn't be consistent. Instead, let's use these. Let's use the addresses actually inside the binary. So let's grab this. So 60 and then 1000. So let's pick an offset inside of there. Let's just call this data adder. P64 OX 60 1000. So that's the start of it. So let's just pick an offset inside of it. That should be good. Now we need a couple pop instructions. So let's actually exit out of Jeff. I don't think we need it anymore. And let me recenter some of these windows so they're a little easier to see. So there's a few ways to go about getting ROP gadgets. You can use Pwn Tools itself, or you can use a tool called ROPR, which I'll be using. I don't think it has a man page, but we'll be using ROPR. If you run it with no arguments, it'll just put you in this like drop-down shell, and you can run commands this way. I've actually never done it through here. So you can easily install it with pip install ROPR, but I already have it installed, so let's actually just run it. We're going to say file write4, and we want to find some pop instructions. I think it's just tac search. Let's look for that pop R14. Loading gadgets from cache. Okay, info, and here we go. Oh, we actually get like a, double jeopardy, right? So we get pop R14 and pop R15. So two birds with one stone. So I'm just going to grab this right here, and we can actually just throw this in here. I know this is getting a little ugly. We can add this as a comment, pop R14 and pop R15. Store it at this address, P64. Nice. Now we just need pop RDI. So let's do the same thing, but this time look for RDI. And then there we have it. It's at this address. And if we actually want to verify this, we could just rerun that GDB command. GDB write4, examine 4 instructions from this address, and we do see it as pop RDI, and then the return, and we can do the same thing for the other one, 690, and we do see it does have pop R15 or R14, R15 in red. So just in case we were suspicious of the tool. Throw this into our exploit. This is optional, but I like having well-commented code. Okay, I think that's the gist of it. I think that's pretty much everything we need. And now we just need to actually put all this stuff together. So let's actually say P equals process. It's called write4. Now we need to start building this stuff. It's kind of disorganized. So payload equals padding. And next we need this pop instruction. So underneath here are the two things that we want to pop into R14 and then R15. R14 will contain that writable memory address. So I call that data adder. Payload plus equals data adder. And R15, it needs the flag.txt. I think this has to be a byte because all of these will be byte strings. Okay, just continue on with our payload. We need the pop RDI instruction. We already have that. And what are we popping inside RDI? That same address, right? And finally, we need to actually call print file. P.sendLine payload. And then to read the flag, print p.receive all.decode. Let me just look over this one more time. It is a little bit ugly. It takes 40 bytes to overwrite base pointer. Writable memory address. Okay. Write what where. Address of print file. Something like that, just so our code is a little bit well commented, so when we come back later down the road, we actually know what we did. So let's save this. I can actually just run this from Vim. Python 3 exploit.py. Failed to open file. Oh no. It failed to open the file. So what did we do incorrectly? What did it not like that we gave it? So let's just review this. So our payload has 40 bytes of padding. Pop R14 and R15. I guess I could run this through a debugger. Let's see if we can manually do it in our head. So into R14, we're going to pop this memory address. Let me double check that that's a correct address. Let's rerun that GDB command, vmmap. Okay, fine. Run, whatever, vmmap. Do I actually need to have a breakpoint? Let's do info proc mappings. So here's the address you want, 601. And we're doing offset 300. That should be fine. Maybe it doesn't like how I'm passing this, b flag.txt. Okay, instead of saying p equals process, what is it? Is it just p equals gdb.attach? I forget exactly what it is. Let me cat out one of my previous exploits. Yeah, gdb.debug. Okay. gdb.debug write4. Now when I run it, it should open it up in the debugger. Awesome. Set a breakpoint. I want to set a breakpoint on read. Disassemble pwnme. All right, whatever. Break star pwnme. Hit C to continue. We're at that breakpoint. Disassemble. Break pwnme plus 133, because that's the offset where read is. So right before we enter our user input, info B, info break. We don't need that first breakpoint. So this is the stack right before we slam in our exploit. So we see that there's really nothing on the stack. 1, 2, 3, 4. So there's a bunch of nulls. There's a bunch of 0. And then we have the base pointer. I'm going to hit NI, next instruction, step forward by run 1. We see we're right about to call read. So now we called read. Here's our 40 bytes of A's. Here's the address of our pop R14, the address of where we want to write to, and then this is like flag.txt. Can I do it like this? Oops, I didn't mean to quit. I meant Control C to copy, not Control C to quit. That's a little annoying. Just rerun it. Do I still have my breakpoints? No. NI. Control Shift C and Control Shift V to copy and paste. Examine string from that address. So it does contain flag.txt, and then there's a bunch of like junk after it. Is that junk? Is that what's screwing us over? Let's hit next instruction a few times. It's about to call put string, NI, nop, leave, ret. So it's about to return here. It's about to return execution to the top of the stack, which is our pop R14 instruction. And you can see that here as well. Pop R14, 15, and return. So NI. All right, so whatever is on top of the stack will be stored in R14. Currently, R14 holds this address. When I hit NI to step forward one instruction, we see that R14 was overwritten. And Jeff does a cool job of it marks everything in red if it changed. So we know the instruction pointer is going to change, obviously. And we know that R14 changed successfully. Now the stack pointer points to this. This might be the problem. Is it because it doesn't have a null byte? Flag.txt and then like these like encoded characters. Is that the issue? Flag.txt question mark. Why is there a question mark? Pop RDI. Okay. Okay. RDI contains this address. Let's examine string $RDI. Empty. Why are you empty? So this value here, it should contain our string. Oh, we didn't do the write what where. So we're about to call print file. So we're calling print file. Hit C to continue. Exit out of this. Failed to open file. Okay. So we never did this write what where. I forgot to include this. So after we actually pop everything inside R14 and R15, we actually need to write it to that memory location. So I think right here, payload plus equals write what where. Because right now R15 and R14 holds the memory address, R15 holds the string, and that's it. So we have to actually take this instruction, where flag.txt is stored inside that address that R14 points to. Let's run it now. In Vim, if you didn't know, you can just do exclamation points and then whatever to run shell commands. Python 3 exploit.py. It's going to open up in the debugger. Let's set that breakpoint. And okay. So this looks a little bit better. Let's step through a few of these. Here we go. We forgot to add this originally. So NI. We see R14. There we go. So R14 contains that memory address that again we got from vmap. It contains this writable address, and now it points to flag.txt. Before it didn't point to anything. It was like null. So let's step through. Cool. So RDI, when I do examine string $RDI, oops, not RSI. RDI contains flag.txt. Awesome. Hit C to continue. I still get a seg fault, but that's okay. Did it print out? Did it do what we wanted? Thank you, filled open file. Let's run this outside the debugger. Q. Okay, so it did print it out. Let's run this outside the debugger. Comment this out. Save and exit. Python 3 exploit. Bang. There we go. There we go. So I forgot to actually add this write4 primitive. Awesome. So hopefully that was fun. Hopefully that made sense. Essentially, all we had to do was be creative because we didn't have that flag.txt stored anywhere. So we need to provide it ourselves and then actually store it inside a writable memory location. So there you have it, guys. Hopefully that was interesting and fun. I will continue on and knock out some more of these ROP Emporium challenges. We're now halfway done. As always, take it easy and see you guys in the next video.